Beneath these mountains, beneath these valleys, and beneath the unexplored terrain of Nepal, there may exist mineral resources that we have never truly mapped. For decades, since exploration depended heavily on expensive field survey, difficult terrain navigation, and years of geological investigation, but today the future is changing. Using the hyperspectral satellite imagery, advanced spectral analysis, and Earth observation technologies, we can now identify potential mineral zones directly from the space. Before going into the actual tutorial, let's deep dive into its actual theory, how we are going to detect the minerals using hyperspectral data. At first, the what actually the hyperspectral data is. The hyperspectral sensor captures the hundreds of the narrow spectral bands, and each material has a unit spectral fingerprints. Like gold has its own spectral signature, copper has its own spectral signature, or the ore that is used to form the minerals has its own spectral signatures, like our fingerprints. And these spectral signatures are used for the minerals mapping, geology, vegetation, and the environmental analysis. And what makes the hyperspectral data so much powerful, right? The traditional RGB imagery only contains the three bands, that is R, red, green, and blue bands. And the multispectral data like Landsat and Sentinel data contains only the limited spectral information. But hyperspectral data like ENMAP provides the continuous spectral signatures that allows us to details the material identification from the space. And what is actually the ENMAP? The ENMAP stands for the Environmental Mapping and the Analysis Program. That is the German hyperspectral Earth observation satellite that captures the visual NIR and the SWIR spectral informations. And after combining these VANIR and the SWIR as a band combination, we can generate the complete spectral signature of the any of the pixels that is used for the mineral exploration and the geological mapping. And what actually the electromagnetic spectrum in the hyperspectral imagery, that is the visible, near infrared, and the short infrared wavelengths are used. And the what make these spectral signature curve is if the minerals is present on the ground, these minerals absorbs and reflect the energy differently than the other places which do not contain the minerals. And the spectral absorption features helps to identify the minerals type. Like, okay, let me go to the okay, this is a spectral signature curve of normal ground. Okay, this is the spectral signature curve of normal ground. Okay, if the minerals is present on the same grounds, then the every spectral signature curve is different. But in the SWIR portion here, and you can see the significant absorption due to the minerals that make us identifying the minerals on the grounds. And how we are going to do the analysis. At first, the ENMAP hyperspectral satellite captures the data set that we are going to download from the ENMAP website, and then at first we apply the radiometric scaling. That means we are converting the radiance data to the reflectance data, and then after we applying the atmospheric correction, and then we apply the multi-noise transformation, and then we find out the pixel purity index of the each of the pixels. And then after n-dimensional visualizer, we are going to detect the anomalous region, and we extract the Endmember from that anomalous region, and then at last using the spectral signature of such regions, we can actually detect what type of mineral is present on such a space. Okay, let's go to one by one. The radiometric scaling contains the raw satellite image contains the digital numbers, and scaling converts the digital number into physical meaningful radiance value, especially essential for the accurate spectral analysis. And then after in the atmospheric correction, we are atmospheric affect the reflectance energy through the scattering and the absorption, and the atmospheric correction converts that radiance distance into the actual reflectance value of the minerals that is present on the surface. And that improves the reliability of the spectral signatures. And then after that we are applying the minimum noise fraction. That means we are reducing the hundreds of the bands of hyperspectral data information into the certain limited information. That means if the ENMAP data contains the information within 224 bands, then we are reducing that 224 information bands into the 30 bands, and then only these 30 band can contains the information of whole 224 bands. That is called the minimum noise fraction transformation. We can do it with the principal component analysis, but here we are going to do with the minimum noise fraction method. And then after we are using the pixel purity index. What actually the pixel purity index is, that identify the spectrally pure pixels. And what is mean by spectral pure? In the remote sensing, we have at least 30 to 30 meter. I am using the ENMAP. It has the resolution of the 30 meter. Within 30 meter, you can say that this is house and this is a road. And this is road, and the data, the radiance value or the reflectance value that is obtained from these pixels contains the reflectance value of both road and the buildings. So what actually we are going to do is we actually the pixel purity index may separate the building reflectance value with the road reflectance value, or find these pixels, these white pixel which contains the only one minerals, only one features, not minerals, only one features. And so PPI identify the spectrally pure pixels, and the repeated random projection are performed here, and the extreme pixel receive the higher purity scores. And after applying the probability from the 0 to 1 and using the threshold, we can get the value like this. And pure pixel represent the potential mineral signatures. And after we rotating these pure pixel PPI value in the one-dimensional visualizer, and then the pixels that is present on the farmost region of this axis contains the farmost axis more likely to be the minerals, and we mark these pixels which are present on the farmost side of this region, and they are rotating something like that far from the every pixels, and these pixels do not contain any of the minerals. And if you can say that how you mark these pixels, and if we rotate these in the n-dimensional visualizer, and you can see that these pixels lies in any instant, right? So that I mark these points. Okay, and after that we extracted the Endmembers. Endmembers are these marked pixels, and these Endmembers, and after we and we check the spectral signature of each of the Endmembers, and then we can find out the spectral signature of each of the Endmembers, and then we can find out the potential location of the minerals. If the let me search, and this is the highest probability of the minerals that is present on this position. And from our study, what we can extract is, if the place contain the minerals something like cerussite, elenite, cavlinite, or all other minerals, there may be the possibility of the presence of the golds. And after I extracting the information, what I found is I found these minerals present on this location, and then I can directly map with that and then I can say that this is the region where the gold is present, right? And then there are the lots of other applications more than the mineral explorations, and you can do other analysis using the minerals. But here in this tutorial, I am specifically directed to how the mineral exploration can be done using the hyperspectral data set. Okay, these are the applications, and these are the advantages, and these are the challenges. These are the large data volume, complex pre-processing requirement, atmospheric sensitivity, and the need for the advanced spectral interpretation knowledge. But I will teach you how you can interpret the result. Okay, let's dive into the actual practical tutorial. First, let's download the data from the ENMAP website. At first, go to your favorite browser and type for ENMAP, and then go to the login page and go to hit login section and enter your credential, and inside hit enter. At first, okay, go to the user portal here and go to the scat1 and insert your own credential and just go for logins. And before login, you have to create an account. So at this time, okay, let's go for the advanced map and search over the area of the interest. I am going to do an analysis over the Pokhara, that is the beautiful city of the Nepal, and I am using this rectangular tool where I am creating the area of the interest, and click over the ENMAP and hit over the search and hit over the hide search map. You can find there are the two hyperspectral data present in this region. I am going to download the first one, so I select the first one and go to the add selected. Okay, click over the add to cart and process to cart and process to checkout and accept the license, both of the license, and click over the continue and hit over the submit button here. Okay, click over the OK, and you have successfully ordered the data, and within a few hours you will get the data set. Go to your email after certain hour, go to the email, check your email data set, and I get the data set, that is the data, and you will get the server as well as the instruction to download the data set. Open the new tab here. I am using Windows, so I am using FileZilla to download the data from the FTP server. Okay. Okay, hit over the download FileZilla for the Windows, and I have already downloaded the FileZilla. You can download from that link, and I have already downloaded. Okay, hit over the FileZilla and open it. Okay, and here you need host, username, password, port to download the data. Okay, I have these information that is sent from the site, sent from the ENMAP. I'm using ChatGPT to decode into the okay, I need, let me see, okay, a host, username, and port. Okay, it give me the host, username, port. Okay, I'm copying the host from this is my host. Okay, I'm just go to the FileZilla. Okay, and paste over it. Username, no, username is, I think, yeah, username is there. Okay, copy the username. Okay, for the password, when you create an account and submit the proposal in the ENMAP, you can set your password. So you use the same password here, and the port is always default 21, and my TLS connection is and getting established here, and I have found my imagery. Okay, right click over it and hit over the downloads. Okay, hit over the download, and if you see here, the download getting started here. Wait until it's get downloaded, and I have already downloaded one imagery for this video, so I will let it download, but I am using the next other data for this purpose, so I'm minimizing it. Okay, and go to the my web, go to my file manager here. Okay, I'm check out all of these and go to the file manager here and go, okay, inside the, yeah, okay, Hyperspectral, Yeah, inside this folder I have this image that I have already downloaded, and the upper one is getting downloaded. Okay, click enter, and you have to go inside, and then you have to extract this file too. Okay, click OK. Yes, and you can see, yeah, I'm using ENVI for this analysis. Let's open the ENVI for this purpose. Okay, and okay, go to the file manager and open the Excel file. Okay, inside, okay, no, go to the D and hyperspectral, yes, and go inside this folder. There is folder, yeah, this folder, and open the second XML file that contains all of the information, and it open the data by separating the visual NIR and the SWIR. You can see in my data manager here. Okay, the VNIR is already open, and if we right click over it and the load over default, you can see the my SWIR band is also downloaded. So I have to stack both of these layer. So input raster, you can select both VNIR and SWIR. Okay, so click over the OK, and the order by wavelength, yes, file, yes, and okay, name over it is stack. Click OK, and then your stack layer is created here. Okay, just wait a minute. Yes, it's completed now, and you can see the whole stack layer. Okay, and if you we have to remove all those bands they which contains the noise. This is the primary step of the hyperspectral analysis. You can use the these are the, yeah, from the, I think, okay, let's see the noise from where the noise started. Okay, I think the band, it is the, okay, let's see in the small steps. Yeah, I think, yeah, 80 and 82 is the starting point, and 95 is the ending point. Okay, I click over it and go to the end. I am using the data without noise, so I go to the file and save as NB and click over the stack and hit over the spectral subset. And okay, I'm removing all of the bands that contain the noise here. Okay, $80 to 95. Okay, I'm removing all of the band which are present between the 80 and the 95. Okay, click over the OK. Okay, yes, and give the file name is okay, stack subset. Okay, stack sampled. Click over the save button. Okay, and now we get the sample data set. Yes, and if we see the spectral signature curve here, you can see the actual radiance curve rather than the reflectance curve. So we have to convert this radiance value to the reflectance value by atmospheric correction. I use quick atmospheric correction tool and to correct for the correction. Okay, and okay, I think the sensor type is generic, but I am accidentally selecting average. So you have to select over the sensor type and make the no, but at this time it's working. And you have to go to the spectral hourglass workflow here and follow all of the step by step here. Okay, and all of the pixel purity index and all the n-dimensional visualizer, all of the terms explained before are actually applying here. And you can see the pixel purity index value here, and as well as the n dimensional visualizer here. If you click over the axis and increase the number of the bands here, okay, and just run that. The main one is spectral hourglass workflow, and all of the pixel that is lies in the most extreme region contains the minerals here. And okay, and I select the end members here. From here automatically this spectral hourglass workflow automatically select the in members and classify the images. And at last you can see all of the mixer tune max filter classes here. And if you go to the invisibility here, you can see the invisibility score images. And I select all of the pixel that is lies in the most extreme region here. Okay, let me search for the pixel which contain in the most extent region. And I can see these red pixel in the right corner here. Okay, and there is a also and all these right pixel contain the location that there may be the possibility of the minerals here. Okay, I just okay, no, I'm not going to exit my workflow here. May need to save the output in the region. I know there is the pixel here. Okay, I'm uncheck all of the region without atmospheric corrected images. Okay, let me select the atmospheric corrected here. Okay, let me go to the generate the spectral signature curve. You can see all of the spectral signature curve, but here you can see the totally different spectrum. If you click over the identify button, you can find the minerals that is present on the you can see elite, muscovite, and budding tunite, and all of these are the ores of the minerals here, you can see. And if you have you can use your own knowledge and find which minerals location is this. And this for today. Thank you so much for watching.